And now M1 V1 final squared 1 plus M2 V2 final squared over 2 plus MGY final 1 plus MGY final 2. They begin from rest, that's a good thing. So no initial kinetic energy, no initial kinetic energy. And we can set this potential energy, that's number 2 to 0. What else do we know?
We could, well, we could set the final potential energy of mass 1 to 0 because we're saying that moves down.
No, we can't.
Or no?
Why?
Oh.
We don't know where it stops. 0.
Oh, yeah.
0 is on this level. It could stop, well, not stop. It travels, each travels distance of 2.4. No, now, yeah, you're right. So if this goes 2.4 meters up, that means we set the length of this rope to a convenient value.
You're right.
It doesn't have to be the same for both, you know, but it could have been. Yeah, because it does not matter. Because what matters, only the change.
Exactly.
Delta Y matters.
Yeah.
So technically you could simplify your reasoning by saying that initial location of the first of the box on the right is exactly 2.4 meters higher than initial location of this. Okay, so in that case, you can make that assumption. So this is 2.4 and this is 0. Because again, delta y of the object number 1 only matters, or the object number 2 only matters. And there is one more very important condition which is missing so far. What do you think should we add as important condition, which we talked about for Atwood's machine? Specific.
I mean, their speeds would be the same,
Absolutely.
Right? Yeah.
Yeah. This is not two different numbers. This is the same number. So now, okay, this will be 2.4 meters. So now you know everything.
Okay.
Yes, literally. Masses. So M1 is a number, M2 is a half of that number.
And to solve for tension, I would just...
No.
No.
So this is what you're supposed to do it.
Right.
Tension, the easiest way is using the Newton's second law. Technically, I'm thinking.
Okay.
I'm thinking.
I mean, I guess if we know speed, then we could...
No, the easiest way would have been using. Actually, I want to check something. How do I do that? Where is my empty slide? Okay. So if I look at this object only, and this object only, we've got force of gravity, we've got force of tension, and it travels down. Let's say it travels down, and its velocity. This object only, kinetic energy changes due to work done by two forces. That is the work done by gravity and the work done by tension.
Mm-hmm.
That's for the object number 1. And for the object number 2, y-axis, the change of the kinetic energy is equal to net work done on that object. So that's going to be 1, That's going to be the work done by gravity acting on the second object plus the work done by tension acting on the second object.
Mm-hmm.
And see, if we add this delta K1 and this delta K2, we'll get what we'll get. We've got what we've got: work on mg, work mg number 2, work tension number 1 plus work tension number 2.
Mm-hmm.
Now the thing is that in this approach, mg2 tension 2, how do I calculate work?
Work equals
Force plus force times magnitude
distance.
times tension force times displacement times cosine of the angle. Number 1 and number 2 in both situations. But
Mm-hmm.
tension 1 and tension 2 have the same magnitude. Distance traveled is the same for both. The only
Right.
difference is this cosine. Tension 2, displacement 2, cosine 2. And in my case, number 1, displacement is down, force is up. This is 180 degrees.
Right.
And in my case, number 2, displacement is up, force is up. This is 0 degrees. So this will be -1, and this will be 1, cosine and cosine. Do you follow?
Mm-hmm. Right.
That is why here these two terms cancel each other out, and we could apply a crescent move. This computer can't handle screen sharing, recording, and points at the same time. Well, anyway, but in this situation, if you want to calculate tension, you can use only law for one object.
Yeah.
Doesn't matter which, because the force of tension comes in the work, and the magnitude is the same for both. And you will know now all these terms. You can extract the information about tension using energy consideration. But again, I would say in this particular problem, that's not the best way. I would use Newton's second law. I think it would have been faster.
Okay. So if this were a problem on the exam, I know we're focusing on work, but if it were an easier, quicker way to use Newton's second law, would that be preferred?
No.
Okay.
Okay. Yeah, I'm back here. So Basically, you have to solve a problem and you have to do what you have to do.
Right. Okay. So if it's saying use energy, just use energy. All right. Okay. That makes sense. Thank you.
You're welcome.
Have a good day.
You too.
Thanks.
No. I wanna. What do I wanna? No, slide show. See, doesn't work. All right. So what we can do is this is a combination of two problems. So first, you are solving for the velocity of this person, of this boy, and then you have to use this velocity to do the projectile motion thing.
Okay.
These are two problems in one. And first, I would set 0 here. No. Can I read it again? Where is it? Come on. Child slides from rest and lands. Okay, so you know the distance and you need to calculate the height of the water slide. All right, so this is what you do know. L is equal to 1.8. L is equal to, well, my number is 2.43, 2.4 meters, doesn't matter. So you have to do this problem backwards. So you know this part, this is the part number 1. From this part, you need to extract information about this speed. And then you have to do the part number 2 to get from speed, which is the part of kinetic energy, go to potential energy to find this height unknown. Well, so the first part is the standard projectile motion consideration. Can you do it energy-wise? Not the best situation. So the initial velocity here is horizontal. Initial x is constant. Initial y is 0 here. And relative to y-axis, this is going to be negative 1.8 meters. That's y final. This is y initial. So y final equals y initial plus initial velocity relative to y component. Negative, well, 9.8 times squared over 2. Negative 1.8 equals 0 plus 0 times time minus 9.8 over 2 times squared. That will give you time. 1.8 times 2 over 9.8. And now, this is also, we call the range. The range R will be equal to 2.4 or whatever number you have, and has to be equal to
Initial
Vs
velocity.
times time. That gives you the initial velocity range over time. 2.4 divided by that square root 3.6 over 9.2. This is how you get this time.
Mm-hmm.
And then you get the speed. And then you go here. And then you say that here you have only potential energy because no initial kinetic. Here we have only kinetic because at zero level there is no potential. So mgy initial should be equal to mv squared over 2. M cancels, so 9.8 times initial, which is what you're looking for. 9.8 times height will be equal to, well, that's range over time squared over 2.
Mm.
This is gives you, this is how you find it. This gives you the height.
Okay, sounds good.
And for the next problem,
That was the very next one, 24.
then this anymore. I'm looking for where the sign from 124. Someone else joined. It's this one.
Mm-hmm.
You should skip it for now.
Okay.
Wait for probably the day after tomorrow. I will solve this problem in the class.
Oh, sounds good. Thank you.
And all other problems probably. Well, no, this could have been done already. Anything with a collision can be done.
Okay.
Yeah.
I'll try.
This problem, yeah, it should go a little bit later in class.
Mm-hmm.
Okay. I will solve it in the class.
Okay, thank you.
Sure. Thank you. All right, so we've got another student. All right, please ask a question. Yes, Stephanie, or my participants. Yes, Stephanie Susan Ramirez. You can ask a question. Can you hear me? Hello? Let's stretch it. So it is very similar to the situation from the class today. All right. The strategy is always the same. You need to first analyze what is happening. So the box was sliding. We had some speed. And it encounters rough section. The length of it is equal to or something. So we know these variables, this and that. We know the coefficient of friction. One, two, three variables. So friction will slow it down. And eventually, after it passes this rough patch, it will keep traveling, having a different velocity. Well, if we need to use energy considerations, we can use law of conservation of mechanical energy, master equation, or work kinetic energy theorem, which are physically identical, mathematically slightly different. And the rule of thumb says if you have any friction, use work kinetic energy theorem. So what does it say? It says change in the kinetic energy is equal to the net work done on the subject. So mv final squared over 2 minus mv initial squared over 2. Work. Well, for work, we need to take a look at the object when it is actually traveling through. So we've got the force of gravity here, we've got normal force there, and we've got force of friction. And gravity doesn't do work. Normal doesn't do work in this case. So the only work done is by friction. And for friction, we know that it has to be equal to, we derive this expression, -1, it's cosine of 100 degrees, coefficient, normal force, and length. That I forgot on Friday. And we can continue now. Because our free body diagram is very simple, normal force is equal to mg, just mg. And now I can look at two sides of this long equation. I can see that I can cancel mass. I can multiply everything by 2, makes things easier. So V final squared minus V initial squared equals -2 mu GL. So V final will be equal to V initial squared minus this combination and square root of that. So final will be less than initial because we have to subtract something, but now I just need to use your values and calculate whatever it is.
Okay. So in the part where you multiply everything by 2, so I didn't think to do that. I just solved for the final kinetic energy. And then I subtracted that by the work done by friction, and I got my velocity.
So right here, physics is done. How do you solve it mathematically? It's completely up to you.
Okay. Yeah, I just wasn't sure. Like, I wasn't sure if I just got lucky when I subtracted, or there was a logic to my subtracting. Because it makes sense when what you're doing with the division by 2.
Well, the problem problem is you could not calculate kinetic energy. That is impossible in this problem because you don't know mass. To calculate kinetic energy, you have to multiply mass and speed squared.
Okay. Okay.
If you got stuck, there is kind of way around, not exactly accurate, but workable. If you don't know mass, it means probably you don't need it. If you don't need it, it means probably it could be any. And if it could equal to any value, you can set it by yourself to be equal to 1, for example.
Mm-hmm.
That should not affect the final value for what you're looking for.
Okay.
Unknown for us also means any. But technically, mathematics tells us that it has to be canceled out anyway. You do mathematics eventually, and then you solve it mathematically. And my equation was mv squared over 2 minus mv initial squared over 2 is equal to negative mu mgl. This was my equation I wanted to solve. And in this equation, I can cross it out. And I can multiply by 2 to simplify it. Both sides of this equation. And then go ahead and finish it.
Okay, that makes sense.
All right, good.
And then I had a question about the practice problem number 9.
All right. The problem number 9. I already have the slides. So this is one of these slides. I want to switch to camera. All right, all right. I want to see what, okay. So you should see the screen now.
Yeah, like the projections.
Can you see me?
Yes.
All right. So for the problem number 9, you have 2 objects, number 1, number 2. When you let them go, one heavy travels down, second light one travels up. What we know is they travel same distance and they have the same speed because of the strain.
Okay.
For each weight, we have only 2 forces acting on it, gravity and tension. Gravity and tension, that's it. So what I could do, I could write the work kinetic energy theorem for the whole system, or I could write work kinetic energy theorem for each weight individually. That's what I did right here. It travels faster and faster, so kinetic energy changes. And the change in the kinetic energy of this object is equal to net work done on this object equals work done by gravity and tension. The change in the kinetic energy for that object is equal to work done by gravity and the work done by tension. Those are two different objects, but the same theorem. Now what can I do? I can write the law for the whole system. If I add this kinetic energy change and this kinetic energy change, this and this, I will get the change in the kinetic energy for the whole system. And what I have is, of course, work done by gravity number 1, then work done by gravity number 2, then work done by tension number 1, then work done by tension number 2. But because tension in the string has the same magnitude and they travel same distance, but in opposite direction, for this object, work done by tension is negative, this is positive, and they cancel each other out. And this is basically the law of conservation of mechanical energy for the whole system. Now, what you're looking for, let me check. You're looking for well, speed probably first, right?
I think it's something like that, yeah.
Yeah. So if you start from using the law of conservation of energy for the whole system, that will give you the speed because they begin moving from rest, and this travels 2.12 distance up, and this travels the same distance down. We actually can choose that the length of this rope is convenient in such a way so when this is up, this goes back to 0. Why not? We can choose it. It doesn't make any difference because only delta y matters. So y will not make our life easier. So in that case, potential energy changes from 0 to this, and this potential from this to 0. And because they travel together, they have the same speed. And in this equation, you know everything except speed. You plug it in and you calculate the speed. And yeah, I remember now. Your first question is speed. Your second question is tension. So for the tension, when you know the speed, for the tension, you can go back to the equation for the box number 1 or box number 2. Does not matter. Because now in this equation, you know everything. You can calculate how kinetic energy changes. You can calculate the work done by gravity. That will give you the work done by tension. And if you know work done by tension, you can calculate tension. I can write it. So the work done by tension will be equal to magnitude of tension times magnitude of the displacement or distance traveled. Well, if we need magnitudes, we can just use magnitudes for everything. So magnitude of the tension will be equal to the magnitude of work done by it divided by the distance traveled.
Why doesn't that have cosine?
Yeah, but it is 1 or -1. So
Okay.
the magnitude of 1 is 1. The magnitude of -1 is 1.
Got it. Okay.
And that value comes from this equation. Or you can choose another equation. It's going to be the same amount of work.
Can you go back to the kinetic and potential energy equation?
That was okay. So this is the law of conservation of mechanical energy. We could use it because of two reasons. Number one, no friction. And number two, as we proved, even tension does individual work on each individual object. It doesn't do work on the system as a whole because it cancels each other.
Okay.
So technically, the beginning of the problem is here on this slide. And then we go to law of conservation of mechanical energy because we know it will work. We solve it for speed, and then we go back to an equation for one object, again, one object to get work done by tension, and then tension.
Okay.
All right.
Okay.
Go ahead. Ask.
So for question 11 on the same work problem.
Yes.
Or the problem set. So
Practice or actual?
The practice that you were looking at. So for question 11B, I got, no, I guess this goes back to the magnitude that you're talking about. So I got a negative value, but my actual value is still the same.
So something is not exactly correct because distance cannot be negative.
Yeah, that's why I was confused because like my number was right, but it's just a negative number. So I was like, oh, that seems weird. So I just put in what I got and it was right, but I'm just confused on how I got a negative.
Well, if you have a number with correct magnitude, you got lucky somewhere. Just a second, it's very small. Takes so much time to process. Okay. All right. I don't know what's happening with this. Is just it is the fastest computer I have, and it doesn't work. The baseball player slides. So frustrating. They claim remote teaching and technology is rudimentary. So 69 kilograms, you know mass starts at 4 meters per second, final is 0, and you know coefficient of friction. Mass initial speed, final speed, coefficient of friction. Work so the work done by friction is negative, but the amount of energy lost, that means we have to calculate the magnitude of that work. And well, for that we have to calculate work done by friction. And for that we know, well, again, this is a problem similar to a box sliding across a rough patch. There is gravity, there is normal force, there is a force of friction, and you have to choose. Do you want to use master equation or work kinetic energy theorem? What did you choose?
The work kinetic energy theorem.
That's what I would do, because friction is not 0. And it says change in the kinetic energy equals net work. And we know it has to be equal to final kinetic minus initial kinetic. And that should be equal to the work done by only friction, which is -1 times coefficient times normal force times distance traveled. Now, this answers part A, this answers part B. For part B, you have to solve an equation. A -1 times mass times initial speed squared divided by 2 should be equal to a -1 times coefficient times normal force times distance. So I don't know what you did wrong, but if you do it right, you must get a positive result.
Yeah, I think I forgot the negative from the initial kinetic energy.
And for the part A, you have to calculate the magnitude of the work done by friction. That will be equal to m v initial squared over 2, also positive. That's it.
Yeah, I think, yeah, I just forgot to carry over the 0, I mean the negative sign from that.
Well, if you know that distance is positive and your distance is negative, you have to start searching for mistake, because the mistake was done, and you have to check one by one every element of your reasoning. And eventually you always find what went wrong, eventually. So, all right.
Yeah, okay. That's all I had.
Okay, so no one else is here. Thank you for your questions. And what I'm going to do, I'm going to stop sharing, I guess. How do I do that?